for now, okay? So I think let's get started. Good afternoon, welcome to another talk of the CIIR talk series. Today it's my pleasure to introduce Alessandro Moschitti, a principal research scientist at Amazon, leading the science behind Alexa's information services. Since joining Amazon, Alessandro has led many projects, including building Alexa's first web-based question answering system. In 2021, he led the development of Alexa's first Retrieval-Augmented Generation, which became the foundation of the Amazon Alexa LLM deployed to millions of users. He currently leads the science for Amazon's local search service with a focus on multimodal LLMs, retrieval, and information grounding for AGI. With more than 25 years of experience, Alessandro's research contributions go far beyond Amazon. He contributed to IBM Watson's Jeopardy Grand Challenge, was a principal scientist at the Qatar Computing Research Institute, leading collaborative projects with MIT CSAIL. He was a professor at the University of Toronto for 15 years and has published more than 350 peer-reviewed papers. He has received multiple IPM faculty and Google Faculty Awards and 5 Best Paper Awards. He has also contributed to the research community through leadership roles such as General Chair of EACL and EMNLP and Program Co-Chair. Please join me in welcoming Alessandro.
Thank you. Thank you for the warm introduction. Thank you for having me here. Today I'm going to talk about understanding RAG-LLM, a practical perspective from web-based question answering. So in practice, in this talk, I'm not discussing the latest findings, but rather it's a bit more retrospective. I can give you a different perspective regarding RAG-LLM to improve your understanding of this technology. Let me start. Okay, so very quickly, the Retrieval-Augmented Generation can be synthesized with this diagram. Given a question, a retrieval system retrieve external knowledge, feed the generative model with this knowledge, and then you can have an answer that can use parametric, so knowledge from parametric knowledge from the parameters of the neural network together with external knowledge. So LLMs, we know that are very powerful, but they hallucinate, especially when they are challenged to answer questions about recent facts or numerical data tables. Retrieval-Augmented Generation improves their readability because you can use the data stored in tables, so LLM can access more accurate data instead of recreating from the parameters. However, ground is good only if the retrieval is a good retrieval, because if we feed the LLM with wrong data, we'll have a wrong answer. But there is also another problem, that when we start to feed the LLM with a lot of correct data, very good data, the information diluted in this context, and LLM can still produce hallucination. So this is a kind of study that has been done in a famous paper, is needle in the haystack kind of experiment, basically. So basically, we still have a lot to understand with respect to grounding an LLM. So in particular, what is really the role of IR in the LLM accuracy? What is exactly grounding? How does it work in LLM? What are the reward functions that are used to train, fine-tune LLMs? How do they really work? and what is the role of automatic evaluation. We have, of course, a lot of papers trying to answer all these questions. In this talk, we follow an alternative path that is based on our practical experience in building faster web-based question answering, and then technology for grounding LLM in my organization. Let me start with the related work on retrieval-augmented generation. So I will mention only the seminal work. So one of these is Lewis et al. Retrieval-augmented generation, knowledge-intensive and NLP tasks. Basically, they use a DPR neural retrieval applied to a Wikipedia index, so the index is quite small respect to real cases that we have nowadays. This means that also the level of noise is low in this kind of experiment, because if you index Wikipedia is much different than indexing the entire web. Another interesting aspect to consider when we read these papers and get the information is that the task takeover was mostly factoid QA. Factoid means that basically the answer is typically an entity or a short phrase. This is critical because when you go to generate an entity, it's much simpler task, less affected by noise than generating an entire sentence, an entire paragraph, and then today's even an entire document or report. There was also experiment on MS Marco, so for non-factoid QA, but basically they didn't have a real system. They took passages from MS Marco, so from Bing basically, and there was no reranking here. Reranking is interesting to test the idea that if the quality of the retrieval is not very high, the performance in generation is actually lower. So in this paper, anyway, using the passages from Bing, so they noted that they could get much better performance than neural IR applied to Wikipedia. Another relevant paper is from Izagard and Grave, 2021, leveraging passage retrieval with generative model for open domain question answering. Also, this is, again, a little bit toy experimental setup because it uses just Wikipedia plus DPR, no reranker that is essential to have a state-of-the-art or at least available grounding system. Again, this was only factoid, so the results that we could derive from this paper are still limited to the fact that it's still not the real task of generating entities. One very positive aspect of this paper is fusion decoder technique that actually allow us to merge 100 of candidates during generation, which is typically a big problem when we want to generate answer using many documents. The third relevant paper is from Glass et al. Retrieve, rerank, and generate. Again, Wikipedia is a main index. DPR used as retrieval together with BN25. Here, the addiction with respect to the other papers is the use of a cross-encoder reranker. And this is an important aspect that will come out in my presentation. When you combine neural retrieval that basically is done with a dual encoder, you pair it with a cross-encoder, which allow to exploit the relationship between question and passages. You have a much better system, so much better grounding system. Still, this was a mostly factoid setting. In the same period, we also published our paper, Answer Generation for Retrieval-Based Question Answering System. We call this system generative QA. And the differences with the other paper is that we used the real search engine that we developed at Amazon, so 10 billion documents about. And state-of-the-art passage sentence reranking, as I will discuss in this presentation, we immediately targeted non-factoid generation. So basically, we had the sentence paragraph in the input and sentence paragraph in the output. So this was, in my opinion, the first real study at a large scale, taking all the challenges. I will present in this presentation other two papers from us. Basically, we improved the generative QA using basically the rerankers as a way to train our model. So, and I will show in the presentation that basically rerankers are sort of reward functions and approximate in some way preference learning like RLHF. And finally, I will also show some results using as a reward function an evaluator to optimize the training of a generative model. Okay, let me introduce now the problem. This is kind of simple slides. We have a question, a modern QA architecture, basically use a search engine to retrieve, for example, web documents. There is a document segmenter that reduces the complexity of long document by separating in passages. For example, here in the example, we separated in sentences, and we will have a top case sentences. Now, for the question, what is Mark Twain's real name? The first candidate is not correct. You mean Simon Logan Clemens, born 30 November 1983, Florida, Missouri. It's a question mark, so this is typically not a good passage for answering the question. And so what you do is to apply a passage reranker, which improve a lot the accuracy of your system. Just a small note on a passage reranking. This is about reranking document fragments that are relevant respect to the query. In previous work, researchers come out with answer sentence selection, which is basically the same things. The only difference that perhaps is targeting a sentence that is smaller than a paragraph. But the really important aspect is that the concept of relevance here is more precise. It's not relevant, it actually answers the question. So in answer sentence selection, basically, we rank passages that provide an answer, a correct answer to the question, not that they are just relevant. And in this way, basically, with the answer sentence selection, you can re-rank the passages, so you can provide the top one as an answer to the customer question. And this is actually what we did in 2019 in Alexa. The technology is very simple. Basically, you need to build a binary classifier that classify what are positive pairs and what are negative pairs. Positive pair means the question paired with the passages or sentence that answer the question. Negative, basically, the passage doesn't answer the question. There was a large body of work on answer sentence selection using different machine learning technique in the past, on three-edit distance-based quasi-synchronous grammar, probabilistic model, CIIR, SVM, lexical model, and so on. And then in 2015, when the neural network started to be the main technique in IR and NLP, we had several papers on using neural network for passage ranking answer sentence selection. And this is just a small part of the literature work that improved just one data set called RAG-QA on answer sentence selection. each of these papers improved the previous state of the art. Just a small view of what happened in that period. So transformers arrived in 2017. I will save time going immediately to the next slide. But basically, what you can do is to add to transformer model a classification layer, the one that you see in the top. Classification layer basically allow you to implement a binary classifier. Before I show you that a reranker is essentially a binary classifier, so you can immediately transform this transformer architecture in a binary classifier, so in a reranker. And you can use a simple cross-entropy loss for this task. So just to recap, what you do for classifying pairs, for classifying pairs, so for deriving reranking answer, you provide the question answer pair for all candidates that you get from the search engine in input to the language model. And then you have a embedding representation that goes in a feed-forward neural network, basically the classification layer. And then you select the candidate that has the highest score, or you can re-rank the candidate based on the scores if you need more than one candidate. Okay, this is a quick recap on the technology. One contribution that we did at the time, because the transformation of transformer in a reranker was straightforward, but basically in the period we didn't have the data. And so we didn't have the specific data for building our answer selector, for example, for Alexa. And imagine that also there was no web-based question answering before, so there was no previous data in Alexa to build the re-rank. So what we did was something that today is challenging, because to train LLMs, they are trying to use several data sets. It's difficult to combine this data set together. Also, at that time, it wasn't clear how to train LLM. Our approach was to have this transfer and adapt technique. Basically, you start from the pre-training language model, then you transfer the language model in a task that is similar to the task that you want to solve, for example, answer sentence selection, and then you do a final adaptation of your classifier, your re-ranker, on the data that is specific to your target domain, and for which you don't have much availability, because this is the problem, that in your specific application, you typically don't have much data. At least this was in that period. And now we can have LLM that can annotate our data, generate our data. So in particular, this is where the kind of size of those data sets, VTQA and TrackQA, you see that we have a few thousand training example, and even hundreds of test examples. And so basically, for example, training an LLM with this data, fine-tuning a transformer on this data was very unstable. The performance were not very great. So what we did was this transfer adapt. So we needed to build the transfer data set. Fortunately, we had Google NQ that was a very big, for the time, very large data set. It was on machine reading, so we adapted the Google NQ to answer selection task. Basically, we consider all the sentences of the Wikipedia pages of the Google NQ data. And if the sentence contained the answer, that would have been, was transformed in a positive answer. All the other answers were treated as negative. So the interesting thing is that here we had a large data set, at least a large number of negatives, is still 60,000 positive pairs. So this was a large data set, especially compared to what we had at the time for the target task. We applied this standard technique. As you can see, this is the plot of the improvement over time of answer sentence selection of the VQA dataset. With our standard approach, we reached more than 90s. Same story for track QA with this standard approach and transformer, we got again more than 90s. So basically, we designed the state-of-the-art ranker, and we could use it for deploying web-based question answering Alexa. Was this good technology? I'm not telling all the story because, of course, in the following years, we built our data, so we improved a lot this reranker. But this was the initial prototype. And is this technology just retrieval ranking good technology? These are some examples of what the system could do already in 2020. So simple question, who was Don Quixote? The answer, I don't even read it as the question is simple, the answer is it's easy. But then the model could already answer this kind of question. Who was the Spanish character, the whatever? The model could generalize and give you the right answer. And this is just a retrieval and re-ranking. Also capture complex relation of the type. Who was that Spanish character had a problem with windmills? The answer is correct. The fictional character Don Quixote is famous for eating at windmills. Then there are other more complex questions. Many layers are in the BERT language model. Which loss function is used for fine-tune BERT? Which ranking loss is used for BERT fine-tuning? And the model was able to answer correctly. So this seems trivial in the large language model era. But what I wanted to stress here is that here there is no LLM. This is just a retrieval and a small transformer model for re-ranking. This part is to set the basis to give you a different perspective of what is a good answering machine. So it's not just LLM. It's mostly about retrieval. And already with retrieval, you solve most of the part. Another interesting things that we learn in that period on building web-based question answering is the concept of context that today we call grounding. So we had a practical problem. We were doing answer sentence selection, and if we have a question on the type, when was Lady Gaga born, we could select the sentence, she was born in 1996. Or what about, I ask, when was Beyonce born? She was born in 1986, is still semantically a good match for the question. So we had a problem with this kind of selection because the model didn't have the context. Or other example of this would be, how is the Bitcoin doing today? You can find a good sentence. The value of a single Bitcoin today is 3,300. Yeah, this could be a good answer, but actually, then if you see in the context, this is an information 2019. And so on. There is also another case in which the context is given by an entire piece of text. So, for example, if you ask how many digits are in PI, currently there are more than 22.4 trillion of digits which show no int, so ending or repeating. This is a good answer, but then you know that this is a good answer referring to pi just reading the entire context. Okay, so for context, at that time we define it as a local context, paragraph level. So the sentences, for example, surrounding your candidate answer. Or there is also global context referring to the entire documents, the rank in the search engine, and TF-IDF, metadata, temporal feature, and so on. So we experimented with context, and for example, with what we call local context. Local context means the sentence. She was born in 1986 on the previous example, plus the previous sentence and the next sentence. And then you encoded this in a transformer like question, previous sentence, answer, next sentence. So this basically is what we do for grounding today. But at that time, we were kind of precise, giving a structure on the grounding and defining precisely what is the grounding for your answer. Because we had, let's say, less powerful model than LLMs. Okay, basically this is the same model, just adding the context. We use Google NQ transformed in answer sentence selection, VDQA that is sentence selection. We also transform squad. I can go fast here because I just want to show you the importance of the context that today I repeat is grounding. So in the blue curve are the model using grounding, the red curve are the model using only the sentence. As you can see, for any data set, for any metrics, there is a large improvement provided by context. Finally, so basically we also deploy this technology to improve the answer to the customer, because before we were making some mistakes with uncontextualized answer, and with this modeling we could provide already a contextualized answer. And now we go in the main part of the presentation, is how all this technology related to what today we call the retrieval-augmented generative LLMs, or simply retrieval-augmented generative QA. And it's interesting, this our part, because first of all, it's before RAG-LLM. And then we build this system following completely different tuition from what came later. Now there is this big LLM that need the information. Instead, our path, as I will explain now, it's totally different. So basically, building this reranker, we noted something interesting. If we take a VQA dataset, also a SNQ dataset, so Google NQ, and we evaluate, we ask a annotator to evaluate the top one candidate, re-ranked by our re-ranker, we can see that the performance for VQA is around 60. For SNQ, it's a little bit more than 70, around 70, more than 70. Interesting, if I ask the annotator to evaluate the top 5, we get 99% for VQA and close to 90 for SNQ. So this basically showed us that there is a big gap between the top 1 selected by the ranker and the top 5. So it means that on the top 5 you have the answer. But actually the ranker, even if it was a state-of-the-art ranker, couldn't select the top 1. So there is this gap around 20–40%, which is very interesting between the top 5 and the top 1. And so in that period, there was a culture in machine learning and NLP of joint modeling. And so what we thought, okay, let's try to model the top 5 candidates in order to select the best one. So instead to select each individual candidate, we select a candidate exploiting all the 5 candidates. And this is typically called joint modeling. So the idea is that we have a primary retrieval feed the pointwise ranker. We have our transformer model, our answer sentence selection. But then we can do something different. We can take pairs of candidates. So for example, out of K, let's suppose that there are 5. We take all the pairs out of these 5 candidates. For example, in this case, we focus on the target answer, and then we pair the target answer with the other 4 or 5 candidates. We embed the pairs, and then we also have an approach to optimize the embeddings using these embeddings in a classifier, but this is not very important. So the interesting that then we can merge all these candidate pairs together with max pooling, and so we'll have a final approach that contains the embeddings of the pointwise ranker plus the joint embeddings among all the candidates. And so this, you create a final classification layer, and then you can re-rank each individual answer with this joint model. This is typical technique. We tried several methods, and we got a good improvement over all data sets. But the idea that improvement was 2-3%. As we saw before, a gap of 20-40%. So there was something that we couldn't understand much, or in other words, any joint modeling done at the sentence level basically didn't fill the gap that we have noted before. And so we had after struggling a lot with any possible joint modeling, we thought, okay, let's have a different idea. So this is a different interpretation of retrieval-augmented generation. So the idea was the following. Let's take a question. How long do you need to go to school for to get a degree in music? Then we have 5 candidates. Among these candidates, there are correct and incorrect. For example, the top 1, in this case, is incorrect. The top 2 is correct, and also the top 4, and the other are incorrect. Now, let's try to think what answer we could write having the knowledge of all these candidates. So an answer could be the average time to get a bachelor degree in music is 4 years. Or also answer B, to get a bachelor degree in music, you need to complete a 4-year program. Now, let's examine the relation between our manually generated answer and the candidate. We see that, of course, the correct candidate has several concepts in common with the answer that we generated. This looks very logical. Also, the other correct candidate has a concept in common with generated answer. Interestingly, also the incorrect candidate have some of the concept in common, because these are, in any case, even if they don't contain the right answer, they are relevant to the question, and so we can still get some important concept, although not the final answer. Finally, it is true that there are some misleading concepts in the incorrect candidate, like 7 and master degree, that has nothing to do with the degree in music. But these are terms that are typically infrequent because they appear there randomly. They are not related, so much related to the answer. And so basically the model has all the elements, reasoning on the frequency of the concept in the candidates, to put everything together and generate the right answer. So this was our idea for joint modeling at the level of concept, multiple candidates input to our generator, with also the advantage that the incorrect candidates will disappear, or their impact will be minor with respect to the good candidate. So basically, pointwise reranker couldn't really decide what is correct and incorrect. The generator instead, exploiting some statistical concept, could come out with a good answer. This is what we did in our paper, Answer Generation for Retrieval-Based Sequential Answering System. We used one of the state-of-the-art generative models, like P5 or Unified QA. And the approach is exactly what I described in the example. We have a question plus the top K passages. And then for MS Marco, we were lucky because MS Marco already provided you with the answer edited by annotators. So basically, this is exactly the training example that we need for our generative system. Question, passages, and the output that is the correct answer. These are the results. It's the same table of before with the generative model. As you can see, now the performance increased a lot, and we feel basically the gap that we noted before. So basically, the generative model is a good joint modeling, is the right joint modeling, and can put together a candidate, even if they can be a bit noisy. Observation, T5 was just less than 800 million parameters. It didn't contain much knowledge. Basically, especially at that kind in 2020, there wasn't much emphasis on storing parametric knowledge. So basically, the parametric knowledge was very minimal. So what the model really learned was to combine candidates, and not much the parametric knowledge that didn't have. And from this, what we can observe for today is that for nowadays is that we can still build a very accurate question answering system using a small LLM with together with an accurate IR system. So we don't need 300 billions model in order to build a very accurate system, but we need to have a good retrieval. Following this research, we had a contribution on transferring the information from the reranker to the generator. And this is interesting to relate to what we do today with reinforcement learning and reward function. So the idea is that given a data set, we can take candidates, and then the answer sentence selection model can re-rank them and also provide some score. So in order to build training data for the generator, we can take the top K plus one candidate. K, the top one will be used as an output, and the other K candidate can be used as an input. And so in this way, we build the same training example that we had before using annotated data set. In this case, the data set is annotated by our reranker directly. We can learn our generative question answering system. Okay, this is good, but we can do even more. We can do more because now we also have the score of the reranker. The annotator is not able to give us a good score, but the machine learning model can. So basically, we can introduce a loss weighting component. Basically, we have the generative loss from the generative model. We can multiply by the probability of the candidates according to our ranker. These are the details, but I don't want to spend time on this. There is also another way to provide weights to the candidates, especially in the input, because basically this weight the candidate of the output. But we can also give a weight to the candidate in the input. We have it, so we have the probability, so we can give some weight. How we do that? We basically bucketize the probability of the candidate in several buckets and associate each bucket with a token. For example, here we have a token B2 that basically tell us the probability of the second candidate. And we can do also, we can also give to the K plus one candidate some weight represented by basically the discretized probability token, this one. Similar approach we can go to, we can use for the input. So the difference, basically we have a bucket, so a token telling what is the probability to the output, sorry. The difference with loss weighting is that loss weighting is something numerical. If you modify the loss. Here you just modify the output text of your target, basically. Okay, so these are the results. Basically, if you use answer sentence selection, you get around 79. If you generate data with the answer sentence selector, we call this weakly supervision, you get even better. So basically, you are able to transfer the knowledge from the answer sentence selection to the trained data to the generator. If you also use loss weighting, you have a better performance because now the model can use the reliability of the output labels, but you can also add the reliability to the input and to the output. And again, you can improve by giving the probability in the input and the output. In testing, if you use all the technique together, you get yet another improvement. And if you add this data generated by the answer sentence selector plus the data of your standard training set, for example, MS Marco, you have yet another improvement telling that this kind of data is complementary. Observation. So the improvement using the weighting in the input show that we need to weight our grounding if you want to improve. So in modern LLM architecture, we can provide grounding. But if we provide the grounding with a weight, the weight tells us how much is reliable the piece of information, we can improve. The weighting on the output, so the loss weighting and also the weighting on the output candidates, it's a reward that we give to our training examples. So basically, this is a sort of preference learning, but without preference. So you give an absolute weight to your output. So this made it basically training very simple before the TPO existed. I can go very fast here because I'm running out of time, and I think I communicated well the concept. You can go beyond the answer sentence selector that provides supervision to your generator, because basically you can use instead of reranker directly an evaluator. The difference between evaluator and reranker is that the evaluator can use also the reference. It's essentially a reranker that can use a reference. And for example, this is an evaluator that we developed in 2023. You provide question, answer, a set of references, and also you can indicate if the reference is positive or negative. So the idea is that you can use the evaluator for augmenting the data, basically creating data set for the generator. And you can do this statically, dynamically, and also use some weighting. So I will show you only the static augmentation because it's also the more performant. Imagine that it's your original data set, and you have a question, a set of candidates, and then the target output, which is the reference. What you can do is to put this information in a generative model. The generative model can generate other candidates. These candidates go in our automatic evaluator because you have the reference, and basically you can label with the evaluator the candidate generated by the generator. And so now you have a set of candidates that are annotated as good or not, and then you can use this candidate to train the generative model. You can do this even dynamically, so at each step you can generate data because your generator is changing. And then you can also add the loss you can modify the generative loss using the probability of the evaluator. Like we did before, you can still do a loss weighting. So you have a great improvement using the static approach, less improvement using dynamic, but this is probably due to the fact that we introduce some noise. But in general, you can get very high improvement on all different data sets. Let's, for example, see MS Marco, the basic model that we presented in the previous paper is about 77. You can improve 10 points. Let me give you the conclusion, because then I can also give you a glance, especially if you ask me for this, on what we are doing on Amazon. So the conclusion of this talk is that, okay, RAG-LLM implements state-of-the-art question answering system. Retrieval is used for providing grounding. Then we have a reward function to train LLM with the RLHF, for example. LLM judge are used for evaluation nowadays, and also for improving the model. In this talk, I gave you a different interpretation of RAG. Contextual passage reranking show basically how the grounding deeply work. Now we saw what are the problems of coreference resolution or ellipsis or other technical problems that you have if you lack of that information. Passage reranking provide multiple answers, while generative system can jointly model them to produce a better answer. So here the idea of this presentation is that LLM, okay, can get, it's very smart, can similarly to what a weaker model like our generator will do. So our weaker model learn to combine answers. So this is probably what LLM is doing, and combining concept based on their probability to be correct is probably what also LLM is doing in a very hidden way. We also show that weakly supervision plus weighting the candidate suggests that you should weight the grounding in RAG-LLM, the different grounding pieces. The weighting of the loss and the output show that the reward function can be also implemented in a different style than just preference learning. Java, that is our automatic evaluator, can provide, again, another type of reference-based reward. Basically, for future, what is the future of what Amazon, but also other companies are probably targeting? So you have several knowledge sources. You don't have only the web. You have the web, knowledge graph, local information, user content, and so on. So you need to retrieve information from each of these different sources. And then when you have this information, a trivial approach is the one to put everything in input to an LLM. But then I mentioned that the LLM will not work very well with all this confused information. So probably the future is to try to structure the information coming from different multimodal and multi-source content. Then LLM can use parametric knowledge to select the right answer among all these structured objects. I think I can stop here for the question. This part is about what we do. So if you ask me what we do, I have another 3 or 4 slides that I can show. But for the moment, I would like to stop here because the talk was already very long. Thanks.
Thank you, Alessandro. Any question? Any question here? Okay, I'll start with one question. So in multimodal RAG, do you have any experience on like what are the main challenges or what are the main bottlenecks? Is it multimodal retrieval or long context of LLMs? Because with multimodality, we can imagine the context size gets longer.
Yes, yes. So basically, there is one basic challenge that is the one that motivated this talk. No, there is noise in the data. Too much context basically confuses the LLM, and if it's multimodal, the confusion increases even higher. Why there is more confusion? For the fact that I was telling before, if you have a different sources, only text, in order to allow a generative model, so even an LLM, to function correctly, you should provide some weights. And different pieces of text can have different weights, but the model can more or less, even without weights, try to understand the semantics and perhaps come out with a reasonable answer. If you have a different modality and you don't give any clue to the LLM how they should be combined and what is their reliability and other structured information, basically other important meta feature, the LLM struggle in provide the right answer. Basically, in this slide, I show that we are working multimodal information retrieval. Here there is the problem how you manage these heterogeneous data types, because you need to make them comparable. So you need to do it at the level of retrieval, and the same problem is at the level of LLM. So basically, one idea to understand problem is that since LLM is a little bit obscure how it works, you can start to understand how a ranker, a multimodal ranker works. There you can understand more directly how the context works, how the different data type works, that you need to make them comparable in order to work. If you do this, then you can also extend what you have learned to, I repeat, a little bit more hidden model, which is the LLM. So, for example, challenges are cross-modal, cross-attention between different modalities. If you have different sources, you use the cross-attention, but then you need to have a cross-attention between image and text.
I see. Yeah.
For example, yeah, this is a simple model that you can use. No, you can use embeddings from text, embeddings from image, but the image has also the text related to the caption. Then what you do a sort of average and you feed forward network. This is an initial model that also works, but it's just the beginning. So this is a very simple model.
Right. Yeah. It would be great to have cross-modal conclusions as well. Any other question from people here or online?
Okay. I have a question. First, thank you for your talk, and I think these are great steps to combat hallucination and ground knowledge. I was just wondering, because personalized AI systems are getting popular, how would you integrate these knowledge groundings into personalization domain? And like, I think one of the challenges would be like learning that heterogeneous representation. What comes to your mind when you want to ground knowledge for personalized responses, but while keeping it personalized, like understanding the user's stylistic preference to that stage?
Yeah, so not that in Amazon, of course, we are very interested in personalization, and I've been working on the field, and there are several aspects. So it's interesting. I can tell you what I think that is the right path and what is the main problem. So basically, personalization is achieved in 3 different stages, perhaps even 4, because LLM may play double role. So the first stage is to collect signals. And already that is a huge problem, no? Because you need to observe conversation of the customer and see what the customer likes, what is worthwhile to store in his profile and so on. There are also explicit selection from the customer, but that is just a small part of what you can do for personalization. So first of all, you need to get the signals. Then, given a question, for example, you need to retrieve those signals. So you need to see if you have some relevant signals for that question that can provide a good personalization, because the other problem is that you cannot personalize everything. So suppose that you have stored correctly the signals, and then you can also retrieve those signals, then there are other 2 steps. One step is to search for that information. And to search for that information, you again have 2 other methods. One method is that you may use LLM to rewrite the query in a way that can retrieve personalized content. That is is very aggressive, because you may end up to bias too much the query, and you retrieve only strongly personalized content that the customer may be interested, but basically you are cutting many other candidates. And the other approach is that instead is softer, because you can train your reranker to exploit personalized signals. So in this way, what I showed you before for context, which was supposed to provide more information on the candidate, can be applied also for personalization. So if in the context I put information about personal preference, I can train a ranker function such that the candidates matching the personalized signals will be put on the top. For example, if I'm looking for Italian food, okay, actually no, I'm looking for a restaurant, and then in my profile I have that I like Italian cuisine. When I ask for a restaurant around me, I give to the retriever and ranker the query, of course, restaurant around me, but I also provide my signals that are the customer likes Italian restaurant. And so in the context, you have Italian restaurant keywords, and then you have the restaurant. And at that point, it's very important how you train the model, because if you train the model correctly, the re-ranker will re-rank even Spanish restaurant in the top, if they are very high quality and very close, but will also rank in higher position Italian restaurant that may be a little bit more far away, but since they are Italian, they need to be shown in the top. So this is the software approach. And there is a lot that we can discuss. So I don't know if I answer part of your question, but there are many other things that we can discuss about personalization.
Thank you. It's good.
I forgot. Of course, the other part is once you have these 10 candidates, Spanish restaurant, Italian restaurant, Asian restaurant, whatever, The other part of the personalization will happen at the LLM level. So the LLM get all these candidates. Also, the LLM knows the personalization signals and may decide to mention the Spanish and then the Italian restaurant, or mention only the Italian restaurant, and so on.
Thank you, Alessandro, for joining us and for the interesting talk. I think we are running out of the time and we want to wrap up, but the students have meetings with you and can follow up on their questions. So let's thank Alessandro one more time.
Thank you. Thank you.
And
I can join the other chat. There will be some faculty members.
Yes.
The other chat.
Yes.
Okay.
It's going to take us a few minutes to go upstairs and join that. So feel free. Thank you.
Thank you. Thank you very much.